Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper from the Hugging Face trending list, published on July 12, 2025, about 4 days ago. This paper proposes a systematic method to determine the optimal data mixture for training large foundation models, providing a principled alternative to costly trial and error. The paper is titled, Scaling Laws for Optimal Data Mixtures, and the implications for how we train these massive models are quite significant. The authors show these laws work across different types of models and can be accurately estimated using just a few small-scale training runs. Alright, so this first figure really sets the stage. We're looking at model loss, which is just a score for how wrong a model's answers are, plotted against the total computation used for training. The chart on the left shows that the predictions from their scaling law, marked with an X, align almost perfectly with the actual small-scale training runs across different data mixtures. Building on that, the chart on the right shows the real power here, extrapolation. It demonstrates that the optimal data mixtures they calculated from small runs lead to the best performance, or lowest loss, even for massive, 8 billion parameter models. So to get those accurate predictions, the authors first have to find the best parameters for their scaling law equation. This figure shows how they chose their optimization method. They compare a standard algorithm called LBFGS with a more advanced one called basin hopping. The basin hopping method, shown in blue, finds a much better solution, a lower fitting loss, with far less computation. This technical step is important because it confirms their method for finding the scaling law parameters is both efficient and reliable, which builds confidence in their main results. So, with that efficient optimization method in place, the authors can now test how well their scaling laws actually work, and that's what we see in these 6 charts. Each plot shows the predicted model loss versus the actual observed loss. A perfect prediction would have all the dots on a straight diagonal line. They test this across 3 model types: large language models, then native multimodal models, or NMMs, which handle text and images together, and large vision models, or L versus Ms. The key result here is the extrapolation. The predictions made from small models, in blue, almost perfectly match the results from much larger models. This table then puts some hard numbers on that accuracy we just saw in the plots. It details the mean relative error, or MRE, which is basically a percentage score for how close the predictions are to the real results. We see this mean relative error broken down for the 2 scaling laws they tested, an additive one and a more complex joint one. The key takeaway here is how small these error numbers are, often well below 1%, especially on the validation data. This really drives home just how precise these scaling laws are across all the different model types. Building on that precision, these next charts show the real payoff. This is where the authors use their scaling laws to predict the best data mixture for a 7 billion parameter LLM, and then they actually train it to see if it works. The 2 plots compare their calculated optimal mixtures against 2 standard ones, a uniform mix and a common one called slim pajama. On the left, the mixture optimized for average performance does best overall. But on the right, when targeting a specific dataset called Open Hermes, the mixture optimized just for that gets the lowest loss. This really shows you can tune the data recipe for a specific goal. Okay, so this table lays out exactly how they set up the experiments to test that extrapolation power. We see the 3 model types again: LLMs, native multimodal models, and large vision models. The columns show the model size, N, the amount of data, D, and the number of domain weights tested. Domain weights are just the different data recipes or mixtures. The crucial part is the split. They train their scaling laws on smaller models, then evaluate them on much larger models, like going from under 1.4 billion parameters to 3 billion for the LLM. This design is what proves the laws work at a massive scale. So that experimental design really sets the stage for the main conclusion. The key takeaway is that these new scaling laws, both a simpler additive one and a more complex joint one, are incredibly powerful. They let researchers predict how a massive model will perform based only on a few small, cheap training runs. This allows them to find the best recipe of data, or domain weights, for a specific goal without having to rely on expensive trial and error. It's a huge step forward for making large model training more efficient and principled. That's all for today. Thanks for tuning in.